Today, we're diving into the invisible infrastructure that pretty much powers our entire modern world. It's this incredible network of celestial roadways, hundreds, sometimes thousands of kilometers right above our heads. Yep, we're talking about satellite orbits, the real highways in the sky.
Have you ever stopped to wonder how your phone knows exactly where you are? Or how we get those unbelievable satellite pictures of hurricanes swirling in the ocean? It's not magic, but it sure feels like it. The real answer is a mind-blowing mix of physics and engineering, a super complex system of routes that satellites are zipping along every single day.
So here's our flight plan for this journey. We'll start with the absolute basics, then we'll get into the rules of the road up there. After that, we'll travel through the different highways, sorted by altitude. Then we'll look at orbits designed for specific jobs, and finally, touch on some really specialized space routes.
Okay, let's start at square one. Before we can talk about all the different kinds of highways, we've got to answer the big question. What even is an orbit? You know, at its very core, an orbit is just a regular, repeating path that one object takes around another. They're locked in this delicate little dance by gravity. But for us today, the best way to picture them is exactly like invisible highways, where each lane is designed for a certain kind of traffic heading to a very specific destination. Now, just like the highways down here on Earth, these space routes have rules. You can't just drive anywhere you want. There are three key things that define every single orbit and control exactly how a satellite moves. Let's break them down.
First up is altitude. Basically, how high is the satellite above Earth? This might be the most important rule of all, because the pull of gravity at that height directly tells the satellite how fast it needs to go to stay in its lane.
Next, we have a fun word, eccentricity. This is just a fancy way of describing the shape of the orbit. If the eccentricity is 0, you've got a perfect circle. But as that number goes up, the orbit gets more and more stretched out, like an oval, or what we call an ellipse.
And finally, inclination. Okay, picture the Earth's equator as a big, flat disk cutting through space. Inclination is simply the tilt of the satellite's orbit compared to that flat disk. So, 0 degrees means it orbits right over the equator, and 90 degrees means it goes right over the north and south poles.
So this brings us to a really important point, and honestly, it's kind of the opposite of what you might think. The lower a satellite is, the stronger Earth's gravity is pulling on it. So to keep from falling out of the sky, it has to move way, way faster. The International Space Station, for example, is absolutely whipping around the Earth in about 90 minutes. But a satellite in a much higher orbit feels less gravity, so it can cruise along much more slowly.
Okay, so with those rules in our back pocket, let's take a trip up through the main orbital highways. We basically group these routes into 3 main zones, all based on how high up they are. Whoa. Okay, the first thing you see here is just the insane scale we're dealing with. Low Earth orbit, what we call LEO, is basically just skimming the top of the atmosphere compared to how far out medium and high Earth orbits are. It really drives home just how big space is.
Let's put some numbers on this. LEO is the busiest neighborhood, home to the ISS and tons of satellites that need a close-up view of Earth. Then you've got MEO, which is the perfect sweet spot for things like GPS. Those satellites take about 12 hours to go around. And way, way out in GEO, that's where you find the big communication and weather satellites, taking a full day or even more to make one trip.
This really nails the main trade-off when you're designing a mission. It's a choice. Do you want to be close and fast but only see a little piece of the Earth? Or do you want to be far away and slow, but get this amazing wide-angle view of the whole planet?
So we've covered the main regions by altitude. Now let's get into the really cool stuff. How engineers mix and match these rules, altitude, shape, and tilt, to create orbits designed to do very specific jobs.
Okay, here's something that trips people up all the time. Geosynchronous versus geostationary orbits. They both take exactly 24 hours to circle the Earth. But a geosynchronous satellite can have a tilted orbit, so from the ground, it looks like it drifts north and south in the sky. A geostationary orbit is the super specific version. It's a perfect circle with 0 tilt, which makes it look like it's completely frozen in one spot. It's the ultimate orbital parking spot.
Now this is a clever one. A sun-synchronous orbit is a special kind of polar orbit, and it's engineered so perfectly that the satellite passes over the same spot on Earth at the exact same local solar time. So whether it's March or August, it'll fly over, say, Paris at exactly 1:30 in the afternoon every single time. This means the lighting on the ground is always the same.
And why is that so incredibly useful? Well, by keeping the sun's angle the same, scientists can compare pictures taken months or even years apart and see the real changes happening on the ground. It lets them track things like deforestation or melting ice caps or cities getting bigger. It's absolutely critical for monitoring our planet's health.
All right, let's wrap this up by looking at a couple of highly specialized routes. These are the ones you use when you have a really unique problem that the standard orbits just can't solve.
You see, a geostationary satellite that's parked over the equator isn't much help if you live way up north in Canada or Russia. So the solution is something called a MEO orbit. It's this super stretched out, tilted path where the satellite swings way out and moves really slowly, just hanging out for hours over those high-latitude areas, giving them a perfect line of sight for communications.
So how does a satellite even get to its final spot, especially one that's really high up? A rocket rarely takes it all the way. It's actually a two-step dance. First, the rocket just drops the satellite into a temporary transfer orbit. Then, when the satellite gets to the highest point of that orbit, it fires its own little engine. That burst of speed pushes it into its final permanent path. It's kind of like merging onto a highway and then hitting the gas to get into the fast lane.
And finally, we have Lagrange points. Now, these aren't really orbits in the classic sense. They're 5 special spots in space where the gravity from the Earth and the Sun balance each other out perfectly, creating these stable parking spots. The L1 point gives you a constant 24/7 view of the Sun, which is perfect for solar telescopes. And the L2 point stays in Earth's shadow, keeping it dark and cold, the absolute ideal spot for telescopes like the James Webb to see into deep space.
So, from the crowded, high-speed lanes of LEO to those VIP parking spots in geostationary orbit, these invisible highways are completely woven into how we live our lives. But as we launch thousands and thousands of new satellites, these highways are getting seriously congested. And it makes you wonder, what's the next generation of these space highways going to look like? And who's going to be in charge of traffic control in the final frontier?